Okay, let's work with problem 1.28. So part A asks us to find the cube roots of 1. And if we take a look at page 17, equation 1.36, we know that any n roots of 1 are given by the formula I2 by k over n, where k can take values all the way up to n minus 1. If k takes the value of n, then the root will be the same as when k takes the value of 0, because when k equals 0, it will be just e to the power 0, and when k equals n, you would have e to the power I 2 pi, which is nothing but these both are the same values. So beyond n, any value that k takes is going to be a repetition of one of the values of k that were less than n minus 1. So this is all very clearly explained in the text. This formula is also derived very clearly in the text. Now, if you want to find the cube roots of 1, all we have to do is plug in n equals 3 in this equation. And that gives us omega equals e to the power I 2 pi k by 3. And k can be 0, 1, or 2. Now, when k equals 0, omega would be e to the power I times 0, which is 1. So one of the cube roots of 1 is 1, not surprising. When k equals 1, omega would be e to the power I 2 pi over 3, because k equals 1, is equal to cos 2 pi over 3 plus I sine 2 pi over 3. That implies omega is equal to 2 pi over 3 is nothing but 120 degrees, and that's negative half, plus I sine 2 pi over 3, which is root 3 over 2. So this is another cube root of 1. So we have one other cube root of 1. Now, when k equals 2, omega would be e to the power I 2 pi times 2 by 3, or e to the power I 4i pi by 3. So this will be so cos 4 pi by 3 is nothing but you can write it as cos 180 plus 60 degrees. So it's going to be negative half, plus I times sine 180 plus 60 is negative root 3 over 2. So therefore the other cube root of 1 is going to be negative half minus root 3 over 2i. So these are the three different cube roots of 1. Now moving on to part B. Explain why the nth roots of 1 when plotted in the complex plane lie on a circle of radius 1 and are separated by an angle 2 pi over n from one another. So what are the nth roots of 1? So omega is given by this value here, right? So we had it here. I'm gonna write it again. Right, so this gives you the different nth roots of 1. Now, what is the magnitude of each of those roots? You can find the magnitude by doing this, right? So that would be times, and this is just going to be 1. It has a magnitude of 1. So every root, when you square the root, has a magnitude of 1. So that implies x squared plus y squared equals 1, right? This is a magnitude. And when this happens, this is nothing but the equation of a circle centered at origin. So when you plot all of these roots in the complex plane, real and imaginary, you'll see that all of those roots, they all lie on a circle where the radius is equal to 1. Now, the other part asks us to explain why all the roots are separated by an angle of 2 pi over n, right? So if you're looking at n roots, they have the form 2 pi k over n, where k goes all the way to n minus 1. Now, let's list the roots explicitly. So they would be e to the power 0, right? E to the power I times 0, e to the power I times 2 pi over n, e to the power I times, sorry, this is going to be e to the power I times, yeah, that's 4 pi over n, and so on. So the phase here is 0. The phase here is 2 pi over n. Here is 4 pi over n. And so on, you will have 6 pi over n all the way until over n. If you take the difference between the phases of the different roots, you will always see that the difference is 2 pi over n. And you can see sorry, this is going to be 2 pi over n. Thus, you see that all the n different roots are separated by a phase of 2 pi over n, which explains why when you draw them in a complex plane, while the radius of the circle is 1, the angle at which they're present, the phase, the difference in phases, there's going to be a root here, which is 1, and there's, let's say there's another root here. So the difference in the phase is going to be 2 pi over n. And that depends on how many roots you have.